So we have done this simple mathematical problem, and we will start with the mathematics behind this support vector machine. So we already have the idea that the equation of the boundary is WTX plus B equal to 0. You see, here I have written WTX plus B equal to 0, which is nothing but the equation of the straight line. Mx plus C, as simple as that, right? So, and also we have understood that the decision rule can be written for any xi. For any xi. Xi means any ith point. Instead of u, now I have written xi. That is the difference here. Okay. Any xi, we can write that predicted y will be either plus 1 or minus 1. What is the criteria? It is plus 1 if w transpose x plus b is greater than equal to 0. And the predicted value of y will be minus 1 if w transpose x plus b is less than 0. So you see, we have definitely a equation of the decision boundary, that is the represented in green, and also we have two support vectors which on to which another two boundary is given, presented in red dot. So basically there are three different straight lines, you can say, over here with respect to 2D. With respect to 3D, there will be three different plane. With respect to a dimension more than 3, you will have three different hyperplane. I hope now it is clear. So let's come to the point, come to the 2D representation, and let's try to understand in 2D only. Just for other, if the dimension increases, only another component will be added in the equation. That is the only difference. So it's not going to be something very huge difference, right? So since we have three different straight line here, we have three different equation naturally. Now something is very interesting to see here. The first thing is that the difference between these two straight line I have considered as D. Now question is that where I have taken this difference? Have I taken here or somewhere in the middle? Where? You see, wherever you take, you can take this difference here or for anywhere if you take, the distance has to be D. What does it mean? It means definitely these two red dotted lines are parallel to each other. Not only parallel, but also it has to be, not only parallel in between each other, but also it has to be parallel with respect to the decision boundary. That is why you see, if the decision boundary is written in this form, WTX plus B equal to 0, the decision boundary, the straight line in the positive side of the decision boundary written as WTX plus B equal to 1, or WTX B equal to minus 1 in the other side. So here two questions come in my mind, in your mind. The first question is that why it is 1? Why not some other value? If it is instead of 1, if it is 10, is it going to harm? This is question number 1. Another question is that why this value in the right hand side both are same? So you see, the reason behind 1 is basically just to minimize the computational complexity. The reason is that what I'm trying to say is that when using this 1 instead of 1, if you have some value, say for example 10, the solution will be just multiplied by 10. That's the only thing. So why I will go for solution multiplied by 10? There's no need to go for a multiplied version of the solution. That's why it's given 1. Now why both are same? The both are same because they are parallel. If you consider it is -2 and it is 1, then definitely they will not remain parallel to this particular decision boundary WTX plus B equal to 0. You can check in your home. So, we just have discussed this one. Now see, what we have understood from this point is that if I want to present, say for example, you see, just for time being, okay, I'm showing you here is that the constraint that I have written in here previously, y pred equal to +1 when WTX plus B greater than equal to 0 and y pred equal to -1 WTX equal less than 0. It means you see here that I will consider y pred equal to +1 when this result is positive. Forget about +1 and greater than 0. See, y pred equal to positive if this multiplication plus b is positive. Y pred equal to negative if this particular equation is negative. Right? What we can do, instead of writing the, you can say the constraint, this is a constraint, right? In this form, we can represent a single equation which can do the same. How? You see, this y pred, if I multiply with WTX plus B, then what will happen? You see, when WTX plus B is positive, then y pred is also positive. That means positive multiplied by positive will be positive, right? Similarly, when WTX plus B equal to negative, less than 0, I mean negative, then y pred is also -1, that means negative. That means here also you will see that y pred multiplied by WTX plus B is equal to positive. That because negative multiplied by negative is positive again. That means as a whole we can say that the constraint, if we put the constraint in a single equation, we can simply write that y pred multiplied by WTX plus B greater than equal to 0. I'm sorry, it should not be 1, it should be 0. You can note it here down in your side. Greater than equal to 0 means positive. It's not possible that this part is positive and this part is negative. It is not possible. Right? Now question is that you see ultimately what I have to do? I have to find out this value of D, and that I want to maximize. So first I have to calculate D and then I will try to maximize that. So let's try to see how we can find this value of D. And it's actually very easy. Because you see, you have 2 points here, assume u1 and u2. Okay. These u1 and u2 you don't know where exist on the line, on the red dotted line. You don't know. But what you have to do? One thing we can do here, since this u1 is on this red dotted line, that's why I can find the equation of u1 just simply by projecting this u1 on w again. Where what is w? W is the perpendicular vector of this particular red dotted straight line. Just what we have done in, I hope you can recall, you have done in previous case here, I think. Yes, here. This W is a perpendicular vector to this particular decision boundary. Similarly, I will have another perpendicular vector W maybe, which is perpendicular on this decision boundary. I mean, not decision boundary, this will be a red dotted margin. So what we have done? We have assumed that we have a W in there, similarly, obviously for this particular red dotted line. And you just project this U1 to W so that you can find the distance of U1. And also I will find similarly the distance of U2. The difference between these two distance is the D, value of D. I hope now it is clear, right? Just I am repeating it again for your convenience, that I am trying to find out the distance between U1 and U2, but you cannot do directly U1 minus U2 because this direction of U1 and direction of U2 is not perpendicular to the straight lines, this red straight lines. It's not perpendicular. There is no guarantee. So what we can do? We can project the vector U1 and U2 on the vector which is perpendicular to this red straight lines. Once we will project them, the direction of U1 and U2 remains same, which is perpendicular to from the origin to the red straight line. Once their direction remains same, becomes same, then simply by finding the difference between those new projected U1 and projected U2 will be nothing but the difference D, right? So let's do one by one. So we have this marginal distance U1 minus U2, but I cannot do directly. What I can do, as I told you, that we have to go for this. We will project this U1 on W. What is W? W is the perpendicular vector which is perpendicular to this straight line red. Obviously, the same vector can be perpendicular to this red because these two red straight lines are parallel to each other. Now here I have written plus 1. Why? Because we are talking about U1 which is lying on red straight lines. These red straight lines which is in the positive side of the decision boundary. That's why W dot U1 plus B equal to 1. Similarly, for U2, I will have something like this. W dot U2 plus B equal to minus 1 because it is in the negative side of the decision boundary. Okay. And what I have to find out? U1 minus U2. We all know that. What I will do? I will simply do a simple subtraction between these two equations. As simple as that. So if I do the subtraction, we all know that subtraction rule. So whatever some sign over here will be, changed, right? Here it is minus 1, so it will be plus. As a result, what I will get? I will get something like this. W dot product of U1 minus U2 equal to 2. Fine. But you see, the thing is that you cannot directly put W in the denominator of 2. Why? Because this W is a vector and this particular vector has some direction involved. Until and unless you omit the direction part, you cannot start calculation, right? So that's why what we do, just to omit the direction, we can what we can do, if we have a vector and if we want to omit the direction, we want to get only the value, what we can do, we can divide that particular vector by the norm of the vector. We all know that. So what we will get, if we just divide it by norm of this in the left hand side, naturally I have to divide the same norm in the right hand side as well to keep the RHS and LHS as same. And once you divide this W by its norm, then this part gets nullified. What remain left? U1 minus U2, which is basically the marginal distance. So my marginal distance is 2 by norm of W, where W is the perpendicular vector perpendicular to these red straight lines. Right? Now here comes. So we have calculated D. We have got, what is D? D is this one. And what is our goal? If you can recall, when we started support vector machine, we said that we want to make this margin as wide as possible, so that we with higher probability we can classify all the points between this distant boundary. So if I want to make the margin as wide as possible, so mathematically how we can express? We can say that we want to maximize this value of D. So what we can do? We can say that that means the objective function can be written something like this, that maximize 2 by norm of W such that Y pred is something like this. But you see, why I have written +1 here and -1 here? Because we don't want to keep any point somewhere within this particular two red parallel line. Remember, because the point, this particular point is the last point to this parallel line. There will be no point available below this red point, red straight line, as well as no point available from this side, which is above this straight line, red straight line. So that's why we are actually trying to maximize this W such that this Y pred will be +1 and -1, which is based on these two parallel margin, and these are the equations of the margin. Either it will be towards, on or after margin, that's why greater than equal to 1, or it will be below this margin, that's why -1. Okay, so this is written here. The constant for the points on or above positive hyperplane is this. Constant for points on or above, sorry, it should be negative hyperplane. Negative hyperplane should be this. I'm sorry, it should be less than equal to. It's written less here, but it should be less than equal to, because it can be on something like this point. It's not mandatory that in this particular hyperplane or straight line, whatever you can say, you will have only one point available. No, you can have multiple points on this red straight line, but no point will be above this straight line available. Okay, so either it will be greater than equal to +1, that means on or above the positive side, or less than equal to -1, that means on or below the negative side, negative margin. As a whole, what we can say? We can say the equation in the same way. We can say, you see, if it's positive and this is also positive. It's positive, it's negative, again negative. So as a result, you can say something like this. Instead of 0, it is now +1. Why? Because again, you see, if you just multiply this Y pred with WTU plus B, you will see that it will be always greater than equal to 1, because equal to 1 means it is on the red hyperplane. Greater than means either below red hyperplane in the negative side or above hyperplane in the positive side. Because I have just rewritten this particular constraint in a single form. That is the only thing that already you have done in a similar way. You have seen. But you see, that mean, we can write it something like that. So this is my objective function, maximizing 2 by W norm such that y prep multiplied by WTX plus B is greater than equal to 1. Fine. But there is an issue. What issue? The issue is that if you look into the gradient descent, you see we have some error. Based on the gradient of the error, we try to minimize the error. So mostly the optimization function tries to minimize something. It's easier to minimize than maximizing something over here. So what we can do? Instead of writing maximize function, we have to represent it as a minimize function, and it's very easy. Why? Because for example, you just assume you have two value a and b. Okay, two variables a and b. So a by b you have to maximize. How you can minimize the just represent the same thing in a minimized way? If you want to maximize a divided by b, it signifies that you want to minimize b divided by a, just opposite one. You can take any value of a and b and you can check in your home. Now that means we have this one, and what we will do, we will simply exchange the numerator and denominator, and we write something like this. So the actual objective function for the support vector machine looks something like this. But here a new term added, you can see, right? So maybe this question come in your mind, what is this? This is what we call a regularization parameter, which is very much useful when we will have outliers, or you can say some just to remove the biasness in the learning, so that the learning will not overfit. You know what overfitting is. So this C and this gamma are two regularization parameter, where gamma is not regularization parameter, I will say it's a error magnitude. We all know what error is, predicted minus actual, and C actually regularization parameter. And what is this? The name regularization, it came from regulate word. Regulate. What regulate is? In your home you have a regulator for on and off, or increasing the speed of fan. You have a regulator. What it does? It basically gives some proper maybe resistance to the fan or something like that, which gives an estimation for the speed of the fan. You can control that. Similarly, this C is also used here to control how much error you want to involve in the objective function. You want to take. If you want to take maximum part of the error, all the error, the maximum value you can keep C as equal to 1. If you want to just ignore the errors of the output, you can simply keep C as 0. So you can have any value between 0 and 1. Now nobody can say that what will be the exact value of C. It's not possible to say. It's actually part of research. Research in the sense, maybe you can check with different values of C, and then you can decide that which will be the optimal value of C for your problem to fit. And for another problem, maybe some C will change, definitely. So this is what we have to minimize, and this is what this object, SVM does. So I hope now the idea is very clear to you, right? But there is still some very important thing is left. In a very small way, I will show that is, you know, till now the problem that we have solved is very much easy and regular. I mean, linear. I mean, you have some set of points here, set of points here. You can have a simple, straight line. You can simply using a straight line, you can classify by 100% accuracy. But in practical situation, the data set is not so straightforward, definitely. For example, I can have a data something like this. You see, we have two classes of data here in the left hand side, where the points lie in this way. The colors signify the classes. I hope you can understand. But interestingly, you see the classes of pink is in both side of the gray class. How you can draw a straight line to classify this? It's not possible. Similar for this case, you see it's scattered. It's actually something like a one class is actually circled over another class. You again cannot create a straight line. So what to do? So in two-dimensional plane, you cannot do a proper classification for both of these cases. In this case, what we do, we transform the data from lower dimension to higher dimension. Okay. For example, let's take an example here from this. So if I transfer the data from low to high dimension for these both cases, it looks something like this. What transformation I have done here, you see? Actually, I have simply multiplied, squared the term. You can say squared. If you squared the points presented on simply on the x-axis, it will become something like this, right? Because square of negative will become square means always positive, which is very close to 0 will be somewhere here in this side, and as it will go towards negative direction or maybe towards positive direction, the squared value will be much more higher. So it looks something like this, and here you will have a chance to get a proper margin by which you can say that above the margin you have one class and below another margin in another class, right? This is for this case. So it's a simple squared calculation you have done on this. But what we have done here, you see, you have presented instead of 2D, we have presented into 3 dimension. And once you are presented in 3 dimension, maybe you can look something like this. If just because of adding one more dimension, the entire projection becomes changed in the space and looks something like this. The ring exists, but because of the third dimension, the distance between the two rings changes, and in between those two rings you can simply put a hyperplane, something like this, as you can see here. Just imagine a hyperplane exists between these two rings, and this hyperplane can easily classify those two rings or the two different classes with linearly, because that is my goal, to find a linear plane or linear hyperplane or a straight line, and that is what I have done. Okay, now question is that how we are doing this transformation. There is a concept of what we call kernel in support vector machine, which actually does this transformation on behalf of you. So once when we will write the support vector machine code, then you will see that we can based on the, obviously the based on the data set, or the, the nature of the data, we can utilize different type of kernel functions for which the, this type of transformation will happen, so that it will be very easier to create a very good support vector machine model for, good accuracy. And there are list of kernels actually. The maybe linear kernel, polynomial kernel, RBF kernel, sigmoid kernel. So these are nothing but different type of functions, the transformation functions. Just like, for example, here I have the transformation function is square. Here can be some another transformation function is given. So similarly, these are different transformation function. This polynomial kernel means it's a polynomial function will be applied on the input data, and a new dimension will be created, a new feature space will be created, where it will be scattered in such a way that you can easily have a linear boundary. Similarly, RBF kernel is a radial basis function kernel. We will learn this radial basis function later, but just for time being, just know this, the name radial basis function kernel. Similarly, we all know what exactly sigmoid function is. Already we have seen in logistic regression. So this sigmoid function can be applied for the kernel as well. So in this way, we can solve our task. So we can stop here regarding the support vector machine, and the basic idea of support vector machine and some maths behind of the support vector machine we have understood. So now what we can do, we can go for a coding, and we can check how this support vector machine we can write, and different data set how we can transform that, we can see. So we can go to the Python code now.